Guys, welcome back. Today we're going to be looking at solving simultaneous linear equations using matrices method. Now, there are a couple of things that I want to point out right off the bat, that when we're going to do this topic, I want to stress on the fact that we're working simultaneous linear equations using matrices method, because if any of the equations is non-linear, then matrices method cannot be used. So it has to be simultaneous equations where both of the equations are linear. So again, we're looking at solving simultaneous linear equations using matrices method, and we're focusing on solving two equations that are linear. If any one is not linear, then matrices method cannot be used. So we're pointing that out. Now, here is an example of two equations that are linear. Now, you would have already been introduced to this in grade 9, and you would have done two methods prior to this. That would have been elimination method or substitution method. Now, we can only do those two methods, or we can only use elimination method when both equations are linear, like in this case. What do I mean? When two equations are linear, or when an equation is linear, it generates a straight line. So each of these equations can actually be written in the form y equal mx plus c, which means if you remember coordinate geometry, for those persons who are doing C-Sec math, if not, you're supposed to be familiar with these from grade 9. But just take my word for it now. Both equations are linear. That means if you were to draw graphs for them, they would give a straight line. Those persons who are doing C-Sec math now would understand clearly what I'm saying from coordinate geometry. The rest of you, you're familiar with those types of equations from grade 9. So I'm going to leave it at that. Now, let's get into the business of solving these linear equations using matrices method. Now, the first thing we want to do is generate a 2x2 matrix from this information. So, what are we gonna ensure that is there before we actually generate this 2x2 matrix? Now, if you look closely at both equations, they are already organized in a way that in both equations, I'm going to call this equation 1, equation 2, that in both equations the x appears first, then the y, and then on the right hand side we just have numbers. Okay, so the equations are so organized that x's are lined up, y's are lined up, and numbers alone are lined up. If they are not lined up, you would have to organize it. What do I mean? For example, if we had a case like this and something like this. Now, clearly, the equations are not lined up because we have x underneath y and we have a 3y over on this side where we should only have numbers. We don't want a situation like this. In order for us to proceed, it must be organized where we have both x's at the front, y is next, and only numbers on the right hand side. This equation would violate that, and we would have to bring over the 3y. Of course, it would be minus 3y, and then we'd make sure that the x is underneath each other and so on. So we'd have to reorganize the second equation. So if you see something like that, organize it like this: x's, y's, and numbers alone on the right hand side. So we're getting rid of that. No. So here we have a perfect alignment of both equations. So we're actually going to proceed with the solution now. So the first thing we have to do is generate a 2x2 matrix using what we call the coefficients of the unknowns in both equations. Now, coefficient means number in front of. So in equation 1, the number in front of x is 2, and here, whenever you're not seeing a number here, then we know by now that it's 1. I hope everybody remember that. In this equation here, 1, and there's a number here in front of the y. So what we're going to be doing is generating a 2x2 matrix. So we're going to say let A equals this 2 by 2 matrix where we're going to use a coefficient. So in equation 1, I'm going to call this equation 1, the number in front of x is positive 2. So I'm going to put positive 2 there. And the number in front of y is positive 1. That goes there. It's as simple as that. So I'm creating a 2 by 2 matrix using the coefficients of the unknowns. Of course, the two unknowns are x and y. And I'm generating a 2 by 2 matrix by simply using the coefficients of the unknowns. Now in equation 2, the number in front of x is positive 1. That goes there. And be careful, be careful, be careful. The number in front of y is not 3, but negative 3. A lot of students mess up that part. So negative 3 comes right there. So now we have that 2 by 2 matrix. I generated it using the coefficients of the unknowns, meaning the number in front of the unknowns. And the number in front of x was positive 2, that went here. The number in front of y was positive 1, that goes here. And the number in front of x is positive 1, that goes there. And the number in front of y was negative 3, and that went there. Straightforward in order. But remember, we could have only done this if it were lined up nicely. X's, y's, and just numbers on that side. All right. So now that we have that, let me push this a little bit further on that side. Now that we have this, what we need to do now is find the inverse of that matrix we've called A. And you can use any letter here. Just say let A equals a 2 by 2 matrix. Now, if we're going to find the inverse, right? As I said before, the next thing is to find the inverse of A. So, in order to find the inverse of A, of course, we need the determinant. The determinant is equal to the product of the elements in the leading diagonal. That is 2 times minus 3. Minus the product of the other two elements, that is 1 times 1. So this will be equal to 2 times minus 3 is minus 6, and 1 times 1 is 1, which gives us a determinant of negative 7. So we have the determinant. The next thing we need to find is the adjoint of matrix A, and that is simply switching these two elements in terms of the position. So negative 3 comes here and 2. Leaving these elements but changing the sign. So there we have the adjoint. All right, so we're going to come back to this. I'm just going to shift this out of the way and come back to this. Now we have that, so we can go ahead now and use the determinant and the adjoint to find the inverse of the matrix. So the inverse of that matrix is going to be 1 over the determinant times the adjoint. Now you can't make any mistake now here, here, or here, because if you make that mistake, there's no way you can solve this. So be careful with negative signs and all of those things here. All right. So the inverse is 1 over negative 7 times the adjoint, which is minus 3, minus 1, and 2. All right, so it simply means you're multiplying all of those elements by negative 1, 7, because 1 over negative 7 is the same as negative 1, 7. So this is simply going to be negative 1, 7 times minus 3, which is the same as minus 3 over 1, negative 1, 7 times minus 1, negative 1, 7 times minus 1, and negative 1, 7 times 2. And that should give us positive 3 over 7, 1 over 7, 1 over 7, and negative 2 over 7. And that is what your inverse is. Now at this stage, because we have bigger fish to fry, so to speak, you don't want to question this. You want to make sure that this is correct. So now would be a good time before you go any further to test if your inverse is correct using the original matrix A, which is this, time the inverse to check to see if you get the identity matrix, which is 1, 0, 0, 1. But if you know that this is correct, proceed. But if you doubt it and you want to check, you can check it using that little rule there that you know already. All right. So we have the inverse. Now here comes the magical part now. Very, 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 very straightforward. Very, very, very simple. Now that I have the inverse, remember, because x came first in both equations and y came second in both equations. This is what you're going to use now to find the value of x and y. Watch carefully. X and y will be equal to, and I'm only writing x at the top because x came first in both equations, and I'm writing y at the bottom because y came second in both equations, which is why it's important to line it up before you even start. So if y came first in both equations, then I would have had y at the top, and if x came second in both equations, I would have had x at the bottom. But this is the organization of the two equations, meaning x came first and y came second. So quickly, xy, or x at the top and y at the bottom, is going to be equal to the inverse of a, which we found already, times what now? Times the two numbers that are on the right hand side, which in this case is -5 and -6, which is why it's important again to make sure that both equations are lined up nicely, x's, y's, and only numbers on the right hand side. So what we have is -5 first and -6 afterwards. So -5 and -6. So what we need to do now, the working out part now is the right hand side. Once we work out this part, then everything is going to start making sense real quick. So let's go ahead now. So x, y here is going to be equal to the inverse, which is this guy over here. So I'm just going to write this. So it's going to be 3/7, 1/7, 1/7, and -2/7 times -5 -6. Now what is happening here is that we're multiplying a 2×2 matrix by a 2×1. And we know that we're good to go because the two inner letters are the same. That means we can multiply, and we should end up with a 2×1 matrix. And a 2×1 matrix essentially looks like this. So we're going to end up with that. So how do we work again? Row by column. So let's work. So this would simply be x, y would simply be equal to 3/7 times -5 plus 1/7 times -6. Correction, -6. So 3/7 times -5 plus 1/7 times -6. So this is a -6 here. And then there are no more columns, so we move down to the second row and start the process again. So 1/7 times -2 plus, -5. I'm rushing a little bit because of the phone issue. So 1/7 times -5 plus -2/7 times -6. All right. So what we have here, let me move over to another page. Let me get rid of this. Slide this over. So what we have here is 3/7 times -5 plus 1/7 times -6. 1/7 times -5 plus -2/7 times -6. So let's see what we end up with so far. So x, y equals, nice and tidy. So you're just multiplying numerators because remember that -5 is the same as -5/1, -6/1, -5/1, -6/1. So we're multiplying fraction by fraction. So what we have here is -15/7 plus this here is going to give you -6/7. Good. Down here, -5/7 plus positive, what that looks like, +12/7. So x and y will be equal to, denominators are the same here, So minus 15 plus minus 6 is minus 21 over 7. My denominators are the same here, so minus 5 plus 12 is 7 over 7. So we end up with here 7 into minus 21 minus 3, 7 into 7, 1. So based on equal matrices, this element here would be equal to that element, and this element here would be equal to that element. So what that means is, therefore, x equals negative 3 and y equals positive 1. And you can see that it clearly makes sense that x is 3 and y is x is minus 3 and y is negative 1, because 2 times minus 3 is minus 6, plus 1 times 1 is 1, so minus 6 plus 1 is actually negative 5, so that makes sense. And minus 3 times 1, because y is 1 there, so minus 3 times 1 is minus 3, and x is minus 3, so minus 3 is minus 6, so it makes sense that x is minus 3 and y is equal to 1. Alright, gentlemen, I want you to review this video as often as possible. Alright, and I hope you found this video insightful, and I'll see you guys on the next video.